This talk was prepared for the ASTM Lubricated Friction Workshop, which took place in December 2019 in New Orleans.
It is perhaps not surprising that many lubricated bench tests tend to focus on the boundary regime, because it is usually the wear or failure that arises under this regime which limits the life of components. However, a well-designed system should not normally operate under continuous boundary conditions unless something has gone wrong, for example with the choice of lubricant. Pure sliding conformal contacts can operate under conditions of boundary, mixed or hydrodynamic lubrication, depending on the entrainment velocity. Pure sliding non-conformal contacts usually operate under conditions of boundary or mixed lubrication, but not hydrodynamic lubrication, with frictional response substantially affected by the morphology of the contact. Sliding rolling contacts, which are by definition non-conformal, operate under conditions of boundary, mixed or elasto-hydrodynamic lubrication. Whereas a bench test may run continuously under boundary lubrication, real systems will only transition through the boundary regime during startup or for a small part of the operating cycle. In the ring liner contact, for example, although the contact may be running under boundary lubrication at top and bottom dead center, a more significant part of the cycle may be operating under mixed lubrication conditions. It follows that if we are concerned with the friction in a real lubricated tribo system, we need to measure that friction under an appropriate lubrication regime. For the most part, for real systems, this will not be in the boundary regime. It is perhaps no surprise that the typical ASTM bias statement for friction coefficient measurement is of the form: the evaluation of friction properties of lubricating oils by this method has no bias because the coefficient of friction can be defined only in terms of this test method. In practice, we tend to use friction measurements in boundary regime bench tests to indicate wear transitions, not to provide us with friction data that can be used to model the frictional losses in real systems. To quote an automotive client, "Our Tier 1 suppliers provide us with lots of friction data, but it is all completely useless as we cannot get it to correlate with anything we observe in the engine." The term friction coefficient implies that the contact in question behaves in accordance with Hamilton's-Coulomb's laws of friction. It is essential to note that these empirical laws only apply to a limited number of simple, dry sliding contacts. Reference to any Stribeck curve should be sufficient to demonstrate that they clearly do not apply to lubricated contacts. Lubricated tribology is sensibly only really relevant to real systems, and it is apparent that such systems operate under a variety of different lubrication regimes. The Stribeck curve provides a useful platform for identifying the operating ranges of many common systems. In a lubricated contact, friction is not independent of sliding velocity. In this slide, it is of course important to note that the devices detailed all have operating points that vary through each cycle of rotation. Lubricant and additive properties affect frictional response depending where we are on the Stribeck curve. It is important to note that it is more or less impossible to predict the frictional response in other words, the shape of the Stribeck curve, from a friction measurement made under just one regime or operating point. This is because different properties are at play. For example, viscosity index improvers, which affect response under fluid film lubrication, have little or no effect under boundary lubrication, and similarly, surface active friction modifiers and other additives, which are effective under boundary lubrication, have little or no effect under fluid film lubrication. Friction is not independent of surface roughness. Plotting the friction coefficient against the specific film thickness, in other words the ratio of film thickness to Ra, or more typically Rq, provides a useful alternative form of the Stribeck curve. If the surface roughness changes, the lambda value changes. This alters the shape of the Stribeck curve. In a lubricated contact, friction is not independent of contact temperature. In the boundary and mixed regimes, where frictional response is affected by lubricant additives, additive activation, adsorption and desorption processes are driven by contact temperature. In the hydrodynamic regimes, temperature of the bulk fluid entering the contact determines the viscosity. Changing the temperature, whether contact temperature or bulk fluid temperature, alters the shape of the Stribeck curve. In effect, one could plot a series of isothermal Stribeck curves if one was so inclined. The law that states that friction is independent of apparent area of contact is more or less true for contacts operating under boundary lubrication. It is not true for contacts operating under mixed or hydrodynamic lubrication. In this example, a line contact specimen is run against a parallel-sided specimen and against a tapered specimen under steady load. With the latter, the contact pressure is double at the narrow end of the stroke compared with the wide end. The doubling of contact pressure does not appear to affect the frictional response. Elasto-hydrodynamic and hydrodynamic lubrication, in addition to requiring the necessary lubricant entrainment velocity, also requires an adequate supply of lubricant and a mechanism for the lubricant to be delivered into the contact. Without these, the contact may end up running under starved lubrication. The limit, without an adequate supply of lubricant, the contact ends up running, regardless of speed, under boundary lubrication. This is one mechanism that can obviously lead to scuffing as the speed is increased. The different contact configurations for sliding or sliding rolling tests affects lubricant entrainment in different ways. With point contacts, entrainment conditions are well defined, but the contact area and the shape may change significantly during tests, altering the entrainment geometry. Similarly, with line contacts, entrainment conditions are well defined. However, with area contacts, entrainment conditions are very poorly defined. How does the lubricant get into the contact? The thrust washer geometry is effectively a sliding face seal, in other words, a system designed to prevent lubricant from getting from one side of the contact to the other. For perfectly flat surfaces, lubricant entrainment is impossible. To facilitate lubricant entrainment, radial grooves must be machined in one surface, as in various designs of plane thrust bearing and in the JSO Suzuki test geometry. A partial journal bearing test geometry looks promising for lubricated friction tests. However, it only works satisfactorily for tests requiring starved lubrication. In a journal bearing, the point of peak pressure is not on the centre line. With a half journal bearing contact configuration, which includes conforming block-on ring, this results in the inlet being closed, preventing lubricant entering the bearing contact. Designers of partial journal bearings address this problem by designing bearings with the required preload and offset. It is possible to produce an asymmetrical contact in a reciprocating test by not allowing the lubricant to spread to both sides of a line contact. This produces starved lubrication in the sliding direction away from the lubricant feed and fully flooded lubrication in the opposite direction, hence different regimes depending on the direction of sliding, hence a direction-dependent frictional response. Now let's consider the influence of contact morphology on the mechanics of the contact. Greenwood and Williamson provides the basis for the modern understanding of the role of surface roughness, hence asperity interaction, in frictional response. The term nominally flat in the title of their paper refers to the fact that the reference plane in their model is flat, but with superimposed surface roughness. In surface profilometry, in addition to roughness, surfaces are usually found to have waviness and form. Whereas roughness drives the frictional response at an asperity level, waviness and form can affect the response at a macro scale. Waviness has a longer wavelength than surface roughness, which is superimposed on the waviness. Form is the general shape of the surface, ignoring variations due to roughness and waviness. Most surfaces are a combination of all three, and all have an effect on the true frictional response and the response of the friction measuring system. Surface waviness modifies the nominal pressure distribution, and both waviness and form can affect the mechanism of lubricant entrainment. How a given contact wears or deforms depends on the relative hardness of the specimens. The shape of the resulting wear track affects the frictional response. The dip in the friction trace towards the stroke end with the wedge specimen is associated with a change in surface topography. It's worth noting that in terms of frictional response, humps have a bigger effect than dips. With a soft ball running on a hard surface, the contact patch remains flat and round. This is readily amenable to analysis of the forces acting on the contact. This is not the case with a hard ball sliding in a conforming wear groove on a softer surface. In this case, we would expect an elliptical contact patch. However, with reciprocating motion, at stroke end, we would expect the ball to conform to the formed end of the wear track, increasing the dimensions of the contact patch in the direction of motion. Exactly this effect is evident in many reciprocating ball on flat tests. ball wear scars showing an elliptical wear scar with grooving in the direction of motion, plus end of stroke witness marks which lack directionality. What effect this change of contact geometry has on frictional response is not clear or readily analysable. If hard ball on soft plate were not an issue, one would expect the frictional response at the same contact pressure not to vary with the size of test ball. It does. Similar effects can be seen with a cylinder on flat line contact. At short strokes, the hard cylinder on soft plate can result in much higher friction than the same cylinder on a hard plate. In this example, with the former, a hole has been dug in the surface. With the latter, the contact patch remains essentially flat. If the test is repeated with the soft plate at a longer stroke, such that the wear on the plate is distributed over a larger area, thus reducing the linear wear depth, the friction response more closely matches that achieved with the hard plate. The frictional response is clearly affected by the flatness of the resulting wear scar. The pin-on-twin geometry provides very clear examples of the effect of wear track shape resulting from a combination of contact geometry and relative specimen hardness on the frictional response. Differences in the shape of the friction loop, instantaneous friction signal, for hard on hard and hard on soft illustrates the effects of contact morphology on frictional response. The hard on hard specimens produce a well-defined spike and essentially square subsequent friction trace, indicating sliding over a flat, unworn surface. The hard on soft specimen does not start with a spike, but ends with the rise in friction. This is a result of the specimen wear and the deformation at the stroke ends. The moving specimen starts each stroke by sliding down a slope and ends each stroke by sliding up a slope. In exactly the same way that real contacts, gears, rings and liners, etc., operate across lubrication regimes, the same happens with reciprocating tribometers. For a given reciprocating frequency, increasing the stroke length increases the peak sliding velocity. At short strokes, the lubrication regime may be fully confined to the boundary regime, where the friction coefficient is usually more or less constant. As the peak sliding velocity increases, the mid-stroke velocities may be high enough to enter the mixed regime, where the local friction coefficient starts to fall. It follows that at longer strokes, hence higher sliding velocities, one would expect the stroke averaged mean friction to be lower than at shorter strokes. This phenomenon can be observed in practice. Now let's consider sliding rolling contacts under boundary and mixed lubrication. In a pure sliding non-conformal contact, it is difficult to separate the many different effects observed as the surfaces wear. In a sliding rolling contact, with the point of contact moving on both surfaces, although the surface topography may change, the apparent area of contact and the contact geometry, hence the entrainment conditions, do not change. If we can design a suitable sliding rolling experiment, we can separate out and explore the effects of parameters such as surface roughness and relative hardness. This adapter was designed specifically for this purpose and uses a simple and low-cost roller specimen running on a flat rail. 2 discs are secured to the roller by grub screws, with the inner faces of the discs locating on either side of the rail, providing axial guidance. Because it is a sliding rolling contact, the contact geometry does not change as the test progresses, as happens in a simple sliding Hertzian contact test. The lubricant entrainment conditions thus remain constant, as does the nominal contact pressure. The roller locates between 2 guide forks projecting down from a reciprocating head. The upper surface of the discs is in rolling contact with the needle roller cam follower, which is loaded from above via a loaded running plate. The resulting slide-roll ratio is determined by the diameter of the roller sample and of the discs. With a hard roller running on a soft flat, the hard roller abrades the softer surface, producing a significant amount of oxide debris in the oil. The hard ground surface remains rough throughout, with the friction levels typically associated with boundary lubrication. The ploughing or two-body abrasive component of friction is dominant. A soft roller running on a soft flat does not appear to produce any oxide debris in the oil. The surfaces run in with a degree of plastic flow and become progressively smoother, with mean friction coefficient, instantaneous friction force, and contact resistance consistent with mixed lubrication. In this case, the adhesive component of friction is dominant. We know that relative surface hardness and surface roughness affect wear mechanisms and wear rates. We should not be surprised that relative surface hardness and surface roughness also affects frictional response. Hence, these parameters must be taken into consideration when performing a lubricated friction experiment. There are 2 further observations that can be made from these experiments. Ploughing, or abrasive friction, requires less energy to remove material than adhesive friction, resulting in more efficient removal of material. Adhesive wear requires more energy, hence higher friction, which we observe at the start of the test. However, after the initial running in phase, the wear ceases and the friction falls. The extreme pressure and anti-wear additives have little effect on the ploughing, or essentially mechanical component of friction, but significant effect on the adhesive component of friction. The results of the sliding rolling tests provide insight into what may be happening with the pure sliding tests, for example, those with a soft pin on a hard twin. With the fully formulated oil, we observe mild abrasive wear transitioning to mild adhesive wear. Here, the additives are preventing adhesive wear, so material is removed efficiently by two-body abrasive wear, and the surfaces become smoother in a controlled fashion. This finally produces a transition to mild adhesive wear, at which point the surface active additives are effective. Adhesive component of friction dominates because the surfaces are smooth. With the base oil, we observe severe adhesive wear transitioning to mild adhesive wear. The severe adhesive wear cannot be prevented because there are no additives. This results in a rapid wear process at the beginning of the test, with material transfer and work hardening of the surfaces. Because the resulting surfaces are rough, the frictional response is dependent on both the adhesive component of friction and the ploughing or abrasive component. Moving further along the Stribeck curve, our sliding rolling contact finally arrives at the Elasto-hydrodynamic or EHD lubrication regime. The simplest way to introduce EHD lubrication is to start with a bit of history, which puts many things in context. There is one key fact to note, which is that H.M. Martin's analysis of lubricated gear contacts, which assumed an iso-viscous lubricant, gave the wrong answer. The calculated lubricant film thickness was far smaller than the surface roughness, so intuitively could not be right. The other point to note is that when the Stribeck curve was conceived, it focused on journal-bearing friction, in other words, conformal contacts. It long predates our understanding of EHD lubrication, and as a result, it has the potential to be confusing if and when we combine the two ideas. The final point to note is that it took more than 50 years to get from Martin's failed analysis to the start of a proper understanding of EHD lubrication. The following example from the now defunct Cambridge Tribology course helps to illustrate the point. This is quite a complicated wedge-on sphere geometry designed to promote rotation of the bucket follower, thus producing a circular wear track. For our benchmark calculations, we use a simplified geometry comprising a cylinder on flat with a 10mm wide contact width. The low Hertz pressure at the base circle suggests that Martin's equation is valid. The high Hertz pressure at the nose suggests that Martin's equation is not valid, and elasticity of the steel and the lubricant pressure sensitivity, quantified by the pressure viscosity index, must be taken into account. Hence, the film thickness must be recalculated using a suitable EHD equation. Only by doing the appropriate analysis can we establish the lubrication regime or regimes under which our components are running, hence determine test conditions in an appropriate model system in which to generate relevant and meaningful friction data. Since the Ertl-Grubin solution, numerous tweaks and improvements have been made to increase the range and accuracy of the calculation, the most significant being by Dowson and Higginson. Further work by Greenwood and Johnson reorganized the EHD equations into three non-dimensional groups, each with identifiable and understandable physical significance. In 1970, Johnson introduced the concept of the Johnson chart, which performs a similar function to the Stribeck curve, but for EHD contacts. This allows the user to identify relevant and appropriate lubrication regimes. As the viscosity and elasticity parameters approach the origin, we have a regime in which the Martin equation is valid, iso-viscous lubricant and rigid solids. In the regime where both elastic deformation and pressure viscosity effects are important, a more comprehensive solution as per the Dowson-Higginson equation is required. The parameter h bar is the ratio of the film thickness calculated taking into account both the elastic deformation and pressure viscosity effects compared with the same calculation ignoring these effects, in other words, the Martin solution. So for our Cam and Tappert example, H nose equals 0.01 microns, the incorrect Martin solution, and H nose using Ertl-Grubin equals 0.186 microns, thus making H bar equal 18.6. But why is this so important if we're only interested in friction or traction in a contact running under EHD lubrication? A journal bearing operating under hydrodynamic lubrication acts as a high shear Couette viscometer, so the friction drag is a function of the lubricant viscosity and the shear rate. It is not influenced by the bearing materials. As we move down the Stribeck curve towards the mix regime, material properties come into play as the surfaces come closer together, and friction measurement is thus useful to investigate the response of different additives, bearing materials, coatings and surface textures in combination with the lubricant. In the case of the rolling and sliding rolling contacts under EHD lubrication, something different is going on. Elastic deformation of the Hertzian contact gives rise to very high pressures, and the lubricant, provided it has been properly entrained and carried into the contact, is subjected to these high pressures. This causes a massive increase in the effective viscosity of the lubricant. This is the pressure viscosity effect, and it can cause the lubricant effective viscosity to approach that of glass. So, under EHD, the solid elements of the contact are separated by an extremely stiff, glass-like film of lubricant. This prevents the surfaces coming into contact and wearing or micro-pitting, but obviously does not prevent the transmission of load across the contact, thus not preventing pressure-generated rolling contact fatigue. It is useful to note that the thickness of the EHD lubricant film is pretty insensitive to applied load, implying that the harder it is squeezed, the stiffer it gets. When it comes to traction between the two sides of the contact, we are clearly dealing with transmission of a shear force through a film of given thickness and pressure-enhanced effective viscosity. When it comes to designing traction experiments, the EHD equations clearly indicate that we have a large potential number of test variables. We are not dealing with a single operating point. The normal convention is to plot traction coefficient, the measured variable, against slide roll ratio, control variable, while keeping other parameters constant. These include load, entrainment velocity, and lubricant inlet temperature. Stepwise variation of these parameters using a two-roller machine then allows three families of traction curves to be plotted to investigate the effects of different loads, entrainment velocities, and lubricant inlet temperatures on the resulting traction coefficient. A key point to note is that if we wish to run experiments at constant entrainment velocity, hence nominally constant lubrication regime, we have to vary the speeds of both test rollers, not just one. We require the same approach if we wish to run experiments at constant slide roll ratio and vary the entrainment velocity. By doing this, we can generate an EHD Stribeck curve with friction or traction coefficient plotted against entrainment velocity. In addition to the test parameters and the test lubricant, the following also affects the traction coefficient: the contact geometry, whether circular, elliptical or line, roller materials, the elastic modulus and Poisson's ratio, the surface roughness, and whether we have any contact spin or skew. The frictional response of a lubricated contact obviously depends on the lubricant properties, but also critically on the lubrication regime and the contact conditions. The lubrication regimes, whether sliding or sliding rolling contact, depend on the entrainment conditions. The lubricant entrainment conditions depend on the contact geometry and the entrainment velocity. The Stribeck curve and the Johnson chart provide us with useful frameworks for determining lubrication regimes and hence placing our friction measurements in the appropriate context. Although friction measurement under boundary lubrication provides a useful indication of wear transitions, it is usually not much help if we are concerned with frictional losses in most lubricated sliding or sliding rolling contacts. Most real lubricated contacts running under steady operating conditions do not run under conditions of steady load or constant sliding speed or constant slide roll ratio. Most tribological tests do. It should be apparent that a time smooth or mean friction coefficient measurement at or about a single operating point with undefined contact geometry and entrainment conditions is not very useful. It should also be apparent that tests that result in significant wear usually result in less reliable and repeatable friction measurements. It follows that it is frequently sensible to run one type of test for friction measurement and another type of test for wear generation. The many parameters that affect frictional response of a lubricated contact make the very notion of a lubricated friction coefficient more or less meaningless.